Okay, so in the last class we were talking about deriving an expression for Vanderwaal's force of attraction between macroscopic bodies. I just want to make a few points clear. One is that when you say between macroscopic bodies, what it actually means is that these are not atoms or molecules, these are things that are much larger than that. Okay. And that means in with this particular course, this corresponds to the interaction between particles which are colloidal in size range. Okay. You should not think macroscopic as really large bodies. Okay. This is what we are looking at is Vanderwaal's interaction between semi infinite blocks, where so the reason why you consider semi infinite block is because when you do this integration, right, I do not have to I do not have to of course, if I assume that there are finite blocks, when I do this integration here, right, I would have another term which will come because of the finite size effects. Okay. So, to avoid these complications, so you assume them to be semi infinite. And the other question that was concerning some of the discussion that we had is that, see, what we are doing here is the pairwise addition of interaction. Okay. If I was doing the pairwise addition of the the interaction forces, okay, which will have units of Newton, then I would have to worry about resolving, okay, this because if we assume that the interactions act along the line that connects these two molecules. Okay. Instead of interactions, if I assume forces, then I would have to resolve that into two components, one vertical and one horizontal, and I would have to, and I think because of the symmetry, the vertical component would cancel each other, and you are going to add only the horizontal component, right. You would have to do that if you are working with if you are deriving an expression for the interaction force, but because we are doing we are working out the expression for the interaction energy, I do not have to worry about this, I just do the pairwise addition. Okay. Now, that is where we had actually stopped, right. So, we had listed down Hamaker constant for different materials. We mentioned that if you take a close look at these entries, metals typically have a very high Hamaker constant. What it essentially means is that if I have a dispersion of metallic particle, they are more prone to aggregation because of Vanderwaal's forces compared to other materials that are listed here. Okay. That is the okay. So, today what we will do is we will try and look at what is called as theories for Vanderwaal's forces based on bulk properties. Okay. And the reason why we want to do that is because the approach that we have followed so far, there are some limitations. Okay. So, essentially the adding together of these molecular interactions that we have done so far, it is an oversimplification. Okay. In this approach, there are several things that are overlooked, okay, because of which this approach may not be applicable for all cases. That means that there could be cases where we may have some limitation in terms of applying these theories. Okay. And again, to give you a few indicators as to what we have kind of missed. Okay. So, if you look at a macroscopic bodies like this, right, and and if it is semi infinite blocks, we said that this Vanderwaal's force of attraction goes as minus 1 over 12 pi a into 1 over d square, right. That is what we derived. Okay. Now, this d is the separation distance, right, that is the surface to surface separation distance. Okay. However, if you look at the these blocks itself, there are molecules that are close to the surface, okay, and there are molecules which are buried underneath, okay, that is buried below this surface. Okay. And we know that in this case, of course, the interaction goes as 1 over d square, right. That means the molecules that are closer to the surface, okay, if I look at the interaction with the molecules on the surface of the two, they will be more stronger. However, if I look at the the molecular buried underneath, okay, they will have a weaker dependence. Okay. Okay. What I mean by that is that if you have any two bodies interacting through vacuum, okay, there is nothing in between the these objects, okay, the molecules near the surface, okay, will screen the interaction, okay, of the molecules that are beneath buried underneath the material. And because you have this inverse power law dependence, okay, the molecules that are closer to the surface will contribute much more to the interaction than the molecule that are buried underneath. Okay. So, this is these kind of aspects were not considered in the derivation that we did. Okay. The other effect that one may have to worry about is that you could have cases where you have particles and on the surface there could be molecules which have permanent dipole. Okay. Now, if you have particles like that, when such particles are sufficiently close, there could be some orientation effects that may come into picture because of the presence of dipoles on the surface itself. Okay. And if you look at Debye interactions and Keesom interactions, which essentially deal with interaction between permanent dipole and permanent dipole and induced dipole. Okay. So, we kind of neglected such effects when we derived expression for when we talked about Vanderwaal's force of interaction. The other issue could be that I mentioned that this is an expression that you can use for calculating Hamaker constant, right. And if I know Hamaker constant, I can actually calculate what is the Vanderwaals force of attraction if I know the geometry of the two objects that are interacting, right. And if I want to calculate Hamaker constant, then I should know beta, okay, and beta may or may not be available for all the materials. Okay, and we know that this beta again in turn will depend on the dipole moments and the polarizabilities, right. If I do not have access to those values, I can't calculate beta, then further I cannot calculate A, and then further I cannot calculate interaction potential. Okay. So, therefore, there is a need to look at theories in which I can kind of relate the Vanderwaals force of interaction to the bulk properties of the material itself. Okay. If I have a material and if I am able to get hold of some physical property or some property that is specific to the material, and if I have a way of measuring it, and if I am able to relate Vanderwaals forces to those properties, then I can have a way of assessing what is the Vanderwaals force of interaction between the colloidal particles, right. So, therefore, there is enormous interest in theories based on measurable bulk properties. Okay. When I say measurable bulk properties, I mean we are talking about properties like surface tension. Okay, there are properties like say dielectric constants and things like that. Okay, if I can measure the certain bulk properties, and if I have a way of relating these bulk properties to the Hamaker constant or the Vanderwaals force of interaction rather than the molecular properties, then there is an interest in doing that because of the limitation that I have discussed so far. Okay. So, we are going to look at some of these theories one by one. Before I do that, I would like to introduce a concept that certain properties of a material they are frequency dependent. Okay. So, for that I have taken an example where so if I see in materials, right, you can classify materials into three classes in terms of their what is called the flow behavior. Okay. Viscous materials, okay, and elastic materials. Okay. These are more liquid like simple fluids that you can think of. Elastic materials are solids, but there are materials which are in between. They are what are called as viscoelastic. Okay. And one of the common example of such material could be something like say paste, for example, or toothpaste that people use, okay, or ointment and things like that. Okay. Now, when you so while you can use for viscous materials, you can use a property called viscosity, right, to characterize its flow behavior. If you have if one works with solids, then you can talk about something called the elastic modulus. Okay. But for materials which are viscoelastic, people talk about something called as a complex viscosity, okay, or something called as a complex modulus. Okay. And the way these measurements are done is, okay, you take we know that whenever you want to obtain any mechanical response of materials, you apply a stress and measure the strain, right. That is what you do, right. Now, if you take like say solids, okay, and if you apply some stress, okay, and look at what is the response, that is strain in the material, then you will see that there is a phase shift between the stress and the strain, and then that phase shift is typically 0, this delta, right. I mean, that means if I have a stress, it will essentially strain will also be something like that. Okay. However, if you do a similar measurements when you apply a stress and then monitor what is the strain for a viscous material, you will see that the stress and the strain are completely out of phase. That means your delta is going to be 90. Okay. However, for these viscoelastic materials, your phase shift is going to be between 0 and 90, and depending upon the extent of phase shift, you can say something about whether the material is closer to viscous behavior or the material is very close to the elastic kind of a material. Okay. And so therefore, what people do is, and I can apply this stress and strain in a sinusoidal way and then measure what is called as a frequency dependent material response. Okay. And that frequency dependent response, it will have two terms. One is what is called G prime, or the elastic modulus, also called as storage modulus, okay, which represents something about the energy stored in the material, because we know that when you take a solid, okay, if you are below the yield limit, right. So, you can if I apply any stress to the material and if you release it, right, I mean so essentially it stores the energy that you apply, right. And similarly, you have a G double prime, which is what is called as a loss modulus or viscous modulus, which represents the viscous component, or it will tell you something about whether how much the energy is dissipated, okay, into the material. Okay. And again, there are ways of measuring it, okay, depending upon whether G prime is greater than G double prime or G double prime is greater than G prime. One kind of tells you something about if G prime is greater than G double prime, then typically these materials are mostly like paste like, for example. Okay. Or if G double prime, the viscous component is more than G double prime, is going to be more liquid like and things like that. Okay. So therefore, there are cases where people are interested to measure frequency dependent properties. I have given an example of a case where the frequency dependent properties are measured for particular material in which you wanted to assess their flow behavior. Okay. Now, this
frequency behavior means you apply force in a
so typically the way these experiments are done is something like that. Okay. I have a like say there is a shaft, okay, and then I have at the end there is it could have like say a disc, for example, okay, and then there is a bottom plate, okay. You put your material here, okay. This is a classic example of what is called as a plate geometry, okay. And then what you do is I have this I have a way of controlling the oscillation. I mean, what I can do is I can take the top plate and I can move it back and forth, okay, and I can do the back and forth movement either slowly or very fast, okay. Thereby I can actually change the frequency, right. Okay. So then you look at if you are doing that in a stress controlled rheometer, what you do is you know what stress you applied, okay, and there are ways by which I can measure the strain, okay. And if I know the stress strain behavior, I can actually back calculate what is G prime, G double prime, G star. There are ways to do that, okay. Now, another property which would be of interest for this particular lecture is something called as a complex dielectric constant, okay, in which again what you do is you take a material of interest, okay, and then you measure the dielectric response, okay, to a periodic variation of the applied electric field, okay, and I can of course change the frequency of the applied electric field, okay, and I can measure what is called as a E star, which is the complex dielectric constant, which will again have two components, epsilon prime and epsilon double prime, similar analogous to what I mentioned earlier. So, there is a storage component, okay, that is the permittivity component that is related to the energy storage, okay, and there is a permittivity component that is related to the energy loss, okay. And if you have a material where E prime dominates, people typically call it as what is called as a capacitive response, because we know that the capacitors are known to storage electric energy, right. There are devices where you can store electric energy, and if E double prime is prominent, people call it as what is called a resistive response, okay, which is the dissipative component, okay. So, with this background, there is one particular theory which is okay. Before I do that, I just want to mention one more important point. So, whenever you have table like this, okay, when you say A is given, there is a list of tables, what this A essentially what it means is that this is the Hamaker constant for interaction between similar blocks, okay, or similar materials. This should actually be A11, okay. That means it is the energy of interaction between like say in this case acetone and acetone molecule, okay, or a block of acetone and a block of acetone, okay, right. And but a more general convention is to write A11 with another number in between, okay. This number tells you something about the medium in which these materials are placed, okay. 0 if it is in vacuum, okay. Therefore, your A should actually be A11 or A101, okay. These are Hamaker constant for interaction of the same material interacting through vacuum, okay. Okay, so there is the first theory is something called as a DLP theory, okay. Again derivation is beyond the scope, but I would like to point to this particular expression, okay. I would like to point to this particular expression because it tells us some nice things, okay. So, when you say A213, that is interaction Hamaker constant for interaction of 2 with 3 and 1 is the medium in between them, okay, which goes as 3 divided by 8 pi square, h is a Planck's constant, okay, 0 to infinity. And so, we have written, so this is the frequency, right. So, we said that if you look at epsilon star, okay, is epsilon 1 in this case plus, for some reason this I is taken inside the, but anyway. So, there is a storage component and there is a loss component, okay. And what you do is, so basically what is important in this case is that, look, I should have measured the frequency dependent epsilon for all the 3 materials of interest, okay. So, once I have access to that, I can substitute that in this expression and I can actually evaluate A212, that is all that is required at this point, okay. Now, the other nice things this tells you is that, look at these numbers, okay. What you have is you have the difference in the dissipative component of, so the one whatever is with I is a dissipative component of the dielectric constant, and what you have is a difference, right. There is a difference in the dissipative component of the dielectric response between the particle 2, epsilon for the particle 2 and that for 1, and similarly that for 3 and that for 1. Okay. Now, because you have the difference, okay, if you have cases where if the dissipative component for dielectric constants match for all the frequencies, okay, match for all the frequencies for 1, 2 and 3, then this quantity can be 0, this quantity can be 0. Therefore, your A213 can indeed be 0. Okay. If whenever you have A212 is 0, your Hamaker constant is 0, that means your Vanderwaal's force of attraction would also be 0. So, therefore, the knowledge that that Vanderwaal's forces are always present, okay, you can defy that, okay, if you are working with materials where for example, there are people who would be interested to look at experiments where the Vanderwaal's forces can be switched off and then look at other kind of interactions. Okay. So, in such cases, some things like this will help you. I can design an experiment where I choose a material 2, 1 and 3 such that the frequency response are the same. Okay. The frequency response of the dissipative component are the same, therefore, your A212 is going to be 0, therefore, I can completely get rid of Vanderwaal's force of attraction. I can look at other effects that you may be interested to study. Okay. So, that is about this DLP theory. Okay. Okay. So, the other approach is to kind of relate this Hamaker constant or the Vanderwaal's force of attraction in turn the Vanderwaal's force of attraction to surface tension. Okay. So, we know we can talk about all of us know about work of cohesion, right. That means, if I have 2 blocks, okay, and if I just bring them together, okay, then because so people typically talk about the work of adhesion or cohesion as 2 times gamma, right, where because you have 2 surfaces you are joining them, okay, right, and this gamma is the surface tension, right. Other way of looking at cohesion process, okay, what do you mean by other way of looking at cohesion for is that I have 2 blocks, okay, I have 2 blocks that are infinitely far apart, I bring them close and I join them. Okay. When I join them, I can think about the distance between the molecules could be some value like say d naught, right. So, we know that if you look at any material, there is some equilibrium separation distance between the particles, right. Okay. Let us think about an experiment, right. So, I have okay, this is an imaginary experiment. So, I have like say a block of water, okay. I have 2 blocks of water, initially they are far apart, I just bring them together and I make a single block. Okay. Now, if I calculate what is the energy, okay. So, so in this concept what is thought about is that I can think about the work of adhesion, okay, as the Vanderwaal's force of attraction between the 2 blocks, okay, in which what you do is, so you initially your materials are separated by like say very large distance. What you do is you kind of bring them close and then join them such that the distance of separation between the molecules is now d naught. Okay. In this d naught is the equilibrium spacing between the molecules of a bulk sample. Okay. So, if I do that, you can actually calculate what is the change in the interaction energy to bring a block from infinity to d naught. Okay. That essentially is minus a divided by 2 pi 1 over d square, because I am considering a case of 2 semi infinite blocks. Okay. Infinity minus a by 2 pi 1 over d square d naught.
So,
Yeah.
what do you mean by equilibrium spacing in this context?
So, in this case, if I have if I am talking about block of water, okay, so we know that because you have various interactions between water molecules, the fact that they are still in the liquid state is because there is some overall interaction energy. Okay. The balance of the attraction and repulsion, all this will give you. So, if you look at like say Lennard-Jones potential, right, if you look at okay, we talked about if you add the two components, so you had something like this, right. So, I am talking about that separation distance, that is the equilibrium separation distance between the atoms that constitute the bulk material.
But here you are talking about the bulk, so the distance is also in like atomic range.
Yes, this is going to be in sub nanometer kind of okay. So, I mean what okay, maybe let us put it this way, right. When this cohesion happens, right, okay, it is a process of bringing two blocks together and then joining them. Okay. Now, if I were to think about what happens between the surface of the molecules that are on one block and the surface of the material on the other block, when you are joining them, in essence what it actually means is that they were very far apart initially. I am putting them together so that the separation distance becomes V naught. Okay. And that separation distance is same as what you had, what the separation distance that there and the separation distance there. Okay. That is the concept, right. Yeah. Okay. So, therefore, the change in the interaction energy is A divided by 12 pi into 1 over d naught square, where d naught square is the interparticle molecular spacing, and the same as I said, the work of cohesion is actually 2 times gamma. Okay. Therefore, I can equate the two, and thereby I can get an expression which is Hamaker constant A goes as 24 pi gamma into d naught square. Okay. And you can actually work a few things out, right. So, if you take for example there is an example that is given here. If you take something like decane for example, okay, C 10H12, right, that is decane. So, typical values of surface tension are about 25 millijoules per meter square or 25 millinewton per meter. Okay, that is the surface tension. So, I have that value, and d naught is the spacing between the molecules. Okay. Typically 0.2 nanometer. If I put in these numbers, it turns out the value of A that I get is actually A is 7.5 10 power minus 20 joules, okay, which is actually very close to what has been predicted. So, at least for simple fluids, if you are working with dispersions which have like say emulsions for example, okay, if I have an emulsion of like say decane droplets in water, okay, if I want to calculate what is the interaction between the two, if you do not have access to the Hamaker constant, okay, then actually I can approach I can go with this approach wherein I know what will be the surface tension, okay, and I know what is the equilibrium separation distance between the molecule that constitute the droplets, and I can actually get A from which in turn, and if I assume that they are spherical droplets, then I can actually go by and say that phi A goes to something like minus A times R divided by 12 d, right. That was a formula that we looked up. Okay. I can actually calculate Vanderwaal's interactions in this way. Okay. So, there are, I mean this is what we have just done, right. So, 24 pi gamma d naught square. there are also approaches where you relate A instead of to gamma, you relate that to what is called as a gamma d, okay, where gamma d is what is called as it is the dispersion component of the surface tension. Okay. What it actually means is that if you look at surface tension in general, okay, there seems to be some, that should be gamma there, okay. This is u divided by 2a square. Okay. So, whenever you talk about surface tension, right, I mean the classic picture that you will see in the textbooks is that, you know, I have a container. If I look at a molecule in the bulk, okay, it is being pulled in all direction, by an equal, force, right. That means, the interactions are kind of isotropic, right. However, if you look at a molecule on the surface, there is only interactions, you can think about the interaction being absent in the outer fluid, right. So, therefore, I can define something like, if the energy of interaction between the molecules in the bulk is u, okay. Now, because of the fact that, if you look at a molecule at the surface, you can say that on average the energy of interaction is going to be u by 2, because it is only interacting with maybe half the neighbors, right. So, now if you know what is the area that the molecule occupies at the surface, I can actually calculate u divided by 2 times a square, where a square is the area that the molecules occupies at the surface, right. Okay. So, you can kind of relate, interfacial tension to the energy of interaction, okay, where u is the energy of interaction between the molecules in the bulk. Okay. If I know that, I can relate surface tension to the energy of interaction in the bulk and the area that the molecules occupy, right. Now, by that concept, what I can do is I can say that the overall contribution for the surface tension comes from the various intermolecular forces. There is a dispersion component, okay. There could be some kind of a dipolar interaction, there could be hydrogen bonding interaction or metallic interaction, so on and so forth. Okay. Therefore, when we talk about the surface tension, okay, one should understand that the surface tension, the contribution to the surface tension comes from various types of interactions that are present for between the molecules of a given substance, and there could be various contribution, and again depending upon the nature of the material that we are trying to deal with, gamma d could be dominant. If we look at as we said, like for non-polar species like decane and other material, okay, then gamma d would be the more dominant species. Of course, if I am going to work with water, then one has to worry about dipole interactions being important, and so people have kind of, this is the overall interaction, overall this is for water, right, the overall surface tension, and these are the different contributions that come from the different forces. Okay. So, therefore, you could actually relate A, which is Hamaker constant, if you are working with if there are cases where several different forces contribute to surface tension, then you would have to consider the dispersion component of the contribution, and then you can calculate what is the Hamaker constant. I just want to briefly, so now these are some tables in which, so we have done this, right. We know how we got that, that is by equating the energy, cohesion energy and the interaction, Vanderwaals interaction between the blocks. This where we considered instead of gamma d, this is one of the expression that we have looked up earlier. This is an expression for the London dispersion forces, okay. And this we looked up earlier, in which we related Hamaker constant to beta and the other material properties, okay. And there are also expressions where I can relate the the polarizability and the permittivity to refractive index and the molar mass and stuff like that. Okay. So, what has been done here is they have calculated. So, this is let me put it this way. This is D naught. So, calculations. So, this is 67 and 68, that is these two. Okay. If you look at so if you know the dispersion component, right, gamma d, and if I know D naught, I can get A by this expression, right, because I know gamma d, I know D naught square, right, and of course, if I so the point that I want to make is that if the value is calculated from this or this, they give comparable numbers. Okay. And again for several materials is what is I wanted to mention. Okay. So you can, the approach that I mentioned, you can use those approaches, and wherever you do not have access to Hamaker constant, you should be able to use one of these expressions and then calculate Hamaker constant for the material of interest. Okay, that is the point. Okay, so there are again people have proposed. So we had expression which is 24 pi d naught square gamma, right? Okay, there. I mean, if you look at this approach, I mean, one wanted to bring in what is called a molecular anisotropy. Okay, if you have, I said the u by 2 by a square, okay, is what gives you in a way gamma, right. Now the a square is the area that the molecule occupies at the interface. Now you could have cases where you may be working with asymmetric shaped molecules. Okay. If you look at molecular shapes, I mean there are objects which can be thought of very close to spherical shape, and there are also cases where you have some non-spherical or asymmetric shaped molecules. Then what d do you consider? Okay, what is the separation distance? Okay, is it the, I mean if you have molecules like this, whether the separation distance between this and this, center to center, or this, so you will have issues finding out what is the actual d that you have to consider. Therefore, there are approaches where I can relate A to the surface tension and Am, where Am is the surface area of the molecule itself. Then I know I do not have to worry about the separation distance. I can relate A to the surface area of the molecule directly. Okay. So, this is one approach where A is kind of related to the surface area of the molecule and the surface tension of the material of interest. Yeah.
Please go back.
Yeah.
So that small a is the not the Am. Am is the surface area of the molecule.
Correct.
A is the surface area of the total.
Now this A.
Yeah.
Oh, then I have not made my point clear. Okay, this A that we are talking about. What is this A? We'll come back. What is this A?
No, not that A. Sorry. The small a. Sorry.
Oh, small am.
Yeah. In the.
This one? Here? No, here A. Oh, this. Okay, let's say here, right?
Yeah.
So this A gamma is 2A 2 divided by, sorry, it is okay u divided by 2A square. Okay. This is actually the area that the molecules occupy at the surface or at the interface.
One molecule or
one molecule.
one molecule.
Yeah. See, we are trying to think about like say we are trying to relate gamma, which is the interfacial tension, to the interaction energy. Okay. Now, if u is the interaction energy between the molecules in the bulk, okay, u by 2, if you assume that there are only half neighbors, then u by 2 is what would be the interaction energy for the molecules at the surface divided by A, because surface tension is defined, you can think about this as energy per unit area, right. This you will have units of energy and the area that it occupies is a meter square, right. So, this essentially energy per unit area, right. There are also approaches where you relate you know now this A goes as 6 am by multiplied by gamma, where am is the surface area of the molecule, and gamma I can relate it to again some thermodynamic properties. Okay, if I know how the internal energy varies with the volume of the material at a constant temperature, and if rho is the number density of the material, I can actually estimate gamma, and I can plug that value of gamma into this expression, and in turn I can calculate A itself. Okay. Yeah.
Em is the surface area of the
Molecule.
No, earlier we were talking about two blocks in your idea.
Yes.
So, like coalescence.
So, see this gamma was a surface tension,
Yeah.
right? Gamma was the surface tension, that we agree, right? So, if you have a cohesion process, 2 times gamma will be the work of cohesion. Okay. So, this is the work of cohesion, and you can think about this as a again work of cohesion will again have a units of energy, right. In this case again it will be energy per unit area, right. And we looked at, right, this again is the interaction energy between 2 blocks. Again this will also have units of again joules per meter square, right. Okay. Now I am trying to relate gamma is the interfacial tension, and I can relate interfacial tension to molecular properties, right, and that is how this was brought in, right. If you look at right, let us okay. So, what you have here is gamma is u divided by 2 a square. So, all I am trying to say here is that gamma in a way is related to the area that the molecules occupy at the surface. Okay. So, let me put it this way, right. Now, say that I have a container, okay. Say that there are 2 molecules in the bulk and the interaction energy between them is u, right. Okay. Now, I say that now these molecules are now at the surface. Okay. I can think about that now. The energy of interaction would be not be the same. Okay. I say it is going to be half. Okay. That is u by 2. Okay. Now, surface tension you can it will have units of millinewtons per meter or joules per meter square, either force per unit length or energy per unit area. Okay. Now, I know the interaction energy between the molecules at the surface, that is u by 2. Okay. I want to get in the area into the picture, and I say that this area is the area that the molecules occupy at the surface.
So that should be half of the.
Hmm?
That will be the half of the. Yeah.
No, I mean yeah, it will be proportional to some length square.
Okay.
Okay.
So that it can be sometime the AM. I mean the
Yeah,
AM is
yeah. So it is some length square. Okay. This is some area, right. Okay. And I am saying that this area is the area that the molecule occupies at the surface. Is that okay?
It is not equal to surface area of the molecule.
So, no, see the surface area. What do you mean? So, say that I have a spherical particle. Say that the molecule that I am considering is spherical. Now, if the spherical molecule is in the bulk, then the surface area is going to be 4 pi r square, right. But what we are interested in is the surface area that it occupies at the surface, the area that the molecule occupies at the surface. That is not pi r square. Okay. It depends on the orientation of it depends on the shape of the molecule. It depends on the orientation, all of those things, right. So, therefore, okay, that is okay. So, in this case your A is related to gamma, okay, times. So, this in a way this AM, right. So, so I essentially have this pi d square, okay, that is essentially an area term, right. and all that is being done here is that, look, if you have cases where you have some complex shaped molecules, instead of worrying about the distance of equilibrium separation distance, you think about the surface area of the molecule. Okay, that is what is done. And now one of the way of getting gamma is to relate that to again some thermodynamic properties, in this case how the internal energy of the material changes with volume at the constant temperature. So, if you have this data, if I know what is rho, I can plug this in this expression and I can get A. Okay. So, the other approach is there are cases where I can relate A, which is the Hamaker constant, to the thermal energy, and VR, which is the reduced volume. And again there are expressions where I can relate, if I know, okay, this section essentially comes from the, if you look at Leonard-Jones potential, right. So, typically Leonard-Jones potential is an example of a 6-12 potential, right. So, where m is equal to 6 and n is equal to 12, I can get from that I can get this parameter, and there are also expressions where I can relate VR, which is the reduced volume, to the the coefficient of thermal expansion, and other measurable properties. So, therefore, there are various theories available where I can relate Hamaker constant to measurable properties, and depending upon the materials that I am working with, I should be able to go back, and of course, some approaches are more suited for liquids, some are more suited for polar liquids, some are more suited for other kind of materials. So, you have to think a little bit about which is the best theory that I should go to when applying them. However, there are guidelines in the literature to look at appropriate theories to relate A to measurable quantities, and you should be able to pick that up and then use them in your calculations to obtain what is the Hamaker constant. Okay. And just to end, people have been able to measure Vanderwaal forces. I would like you guys to go back and read up some papers in the literature. There is something called as surface force apparatus, okay. And what is being measured here is force divided by radius as a function of distance, okay. Force divided by radius. I will just go back to that expression. So, we had that in one of the classes, right. So, if you look at this interaction force, okay, between where was that? So, that was here, okay. If you have two flat plates, the interaction energy was A divided by 6 pi d cube, right. A divided by 6 pi d cube, right. Now, okay, so that is your force, right. Now, I can, so therefore, so if you look at this is the measurement. So, this the data point that you see, that is the filled circles, open circles, and other experimental data that have been measured. You have been able to measure force as a function of distance, and that line is a fit. Okay. So, which so there are direct measurements of Vanderwaal forces which people have been able to measure, and it kind of complies with this is actually done between two flat mica sheets, okay, and they are separated by a distance d. For several distances, you basically get these force versus force divided by radius, and then plot that, and it looks like it actually follows what has been predicted by theory. Okay. So, maybe I will stop here. So, the next topic that I want to do is to look at effective medium on the Vanderwaals attraction. Okay. So, instead of vacuum, if you have air between the particles, or if you have some other fluid between the particles, how would Vanderwaals force of attraction be altered, is what we are going to look at. So, thanks.